Welcome back to Designing AI-Driven Personalized Learning Environments course. In this video, we will talk about Bayesian knowledge tracing. Bayesian knowledge tracing is again the continuation of the Bayesian network. Consider we want to update a node called concept C to indicate whether the student learned the skill or not based on the responses on the questions. Okay. If you have a node for student's response, no student's response to a question can be Boolean value is or yes. How do you update it? Before we go, let's do some activity. If the student response to the particular question is correct, then increase the response if the response is 1, or if the student's response is 0, you decrease the student's knowledge on the concept, right? So basically what do in Bayesian network, if the response is correct, you might have better probability the student might know concept. If the response is wrong, you might reduce it. Write the one drawback of above method and update the student skill on concepts. How is this correct? Is this method correct? What is the one simple drawback in this particular scenario? Please pause this video after writing down, after thinking about it, then continue. The thing is, in the previous idea, we are kind of missing the student guessing the right answer or student slipping, which means after even knowing the answer, they might have small mistake in it. Those are the problems we are missing it. Also, we did not consider the transition from one state to the other state. The student was in unlearned state, now we move to learned state. That is this dynamic, T1 to T1 plus 2 or T2, something, the state change is missing. So in a Bayesian knowledge tracing, these 4 variables are very important. It is not just student have answered the question wrong, instead it is all about students is guessing, slipping, does the transfer happened or not. These are the values you have to look at it. So the initial probability or the prior knowledge is basically the based on the prior knowledge. In our questions in the Bayesian network, the prior knowledge on knowing the explanation P EA is equal to 0.01 or 0.2, that is the initial probability. Or in the sum we solved, we assume that initial probability is 0.05 because we don't know student knows the knowledge, we assume 0.5. So the prior knowledge will be assumed to the initial knowledge. Please ignore this KU for now because that is, if you want to read, you go read the new paper completely. For this particular video, we will not go into that. So you are building an intelligent tutoring systems for 2 different subjects. Consider that. Compare multiple choice question. There's 4 options are there, A, B, C, D. Or other system have write a code in Python syntax. Okay, one system we are asking the students to read the statement, read a lot of things, and answer set of 5 MCQs. In other scenario, you ask students to write a code in Python syntax. That's all. Which of the statements about the BKT parameters is true? For example, in a Python question has a higher guess than a multiple choice question. The multiple choice question have a higher guess value compared to the Python question. The slip is always 0.5 for both. The guess parameter is irrelevant if the student answers correctly. Think about the 4 options and select one of the option, then continue to watch. Of course, this multiple choice question have the higher guess probability because it's in 4 options, one option will carry 0.25 probability. So guess will be more X compared to the Python question, because Python question you have to write a syntax. It's not possible to guess it without knowing the knowledge. There's high chance you could guess without knowing any concept in the MCQ. So that's clear. That's what we want to bring in. What is BKT? What is guess parameter? What is slip? We'll see slip. So how do you measure the probability of learning if the response to the question is correct or equal to 1? Now we wanted to measure the response to the question or is correct given the value. So in a previous case we used the Bayes network where we said that if the student response is correct, there's high probability the students knowing the concept also high. But how do you do that now? Because now we introduce 2 different concepts, that is guess and slip. Consider this and try to come up with the how do you update it now. So that we will see in this video. If probability of response, and this is the Bayes theorem where probability of response equal to 1 given the learning, then probability of learning in general, then probability of response equal to 1 in general, adding both probabilities. But the response equal to 1 is possible only the student knows the skill and not slipping, or not knowing the skill and guessing. I hope it's clear. For example, student is to update this. The student response 1 is possible. 1 is possible. Student knows the skill. Okay, I would student have the skill. No skill on the particular concept. If student have the skill and not slipping, okay, then the response will be 1. Students have the skill and not slipping, or student have no skill but guessed it properly. Okay, the student have a no skill, literally no skill, but is able to guess it properly. The response 1 is possible, student have the skill and not slipping. Kind of this one, I am just putting it like this, kind of not having slip and have the skill, or no skill when guessing. Okay, so that's the, when will this response will be 0? The student have the skill and slipped it, okay, or student have no skill and not able to guess correctly. Probability of guess is also 0. Then the student will have no score. The student have no skill and not guessing properly, or student have the skill and slipped it. Is it clear? Student knows the skill, L into slip. That is the case, the student will get a response equal to 0, or students have no skill and no guess. Clear? This is the two possibilities that you should consider. Response 1 is possible. Now, how do I include these values in updating the learner's knowledge? So here the knowledge is basically learning and not slip, or 1 minus p not learning and p equal to guess. If it is correct, that is observation equal to correct given learning, and probability of learning given observation equal to correct. So we will use this formula to compute the students learning by given observation. So if you look at it, this is the formula for the answer is correct. Okay, how we will just look at it how it is possible. So there are two ways a student can give the right response. One is students knows the skill and no skip, no slip and skill is good. Okay, no skill and guessing, we saw this in the previous. Given this, student is knowing the skill and not slipping, that is the probability we are going to compute. This is a probability the student could give the right answer knowing the skill and not slipping, also without knowing given guessing. Given that we want to measure only the student knowing the skill and not slipping is our interest. We don't want to know about students not knowing the skill and guessing it. So this is the ratio, that is a probability you are going to measure. This is a probability to update students' knowledge based on student knowledge and slip value. Okay, so I hope it is clear. For the incorrect one, this will be a bit different. For example, student knows the skill but slipped. Okay, student don't know the skill, don't know the guessing. So student knows the skill and slip, it can be the incorrect one also. So we are not considering student not knowing, you know, and guessing it here. Saying the student knows the skill but slipped it. What is the probability? Student knowing it but slipped it. There's a chance, right? So that is what we want to update on the student's wrong answer. Now for the opposite. I hope it is clear that here we want to measure student knows the skill but slipped. What's the probability? That's why we are going to measure this, the second one. Similarly, a student not knowing the skill and not able to guess also possible. So that is also another set of probability will come. That is another set of probability table we could create it. So in the Bayesian knowledge tracing, what we are doing is that using this Bayesian network, that the concept is there, we are measuring a lot of questions. Based on the answers, we are also considering slip and guess to update the student's knowledge. In a previous Bayesian network, we updated only assume that there is no slip or guess. In this case, we are trying to include slip value also. That is the only value. So together, if I want to update the, you know, the current state of the learners from the, you know, for the next state t plus 1, we will take the value of, you know, based on observation, can be right or wrong, what is the learning, plus what is the opposite, like what is the not learning that we not measured actually. Into the transition, we said that acquisition, P of T is acquisition, how much knowledge is kind of acquired from this reading this particular content. This can be set into a fixed value based on the designers or the experts. So this is how the Bayesian knowledge tracing is updating the students' mastery or the set of questions. Here the idea is that in the IRT, it's just given a set of answers. I will update after 10 questions student learner abilities say one value. But in the Bayesian knowledge tracing, we will be updating based on their responses to each and every question. We update the corresponding skill. The idea is that each question is measuring one particular skill. That is the idea of the Bayesian knowledge tracing. I hope this is clear what is Bayesian knowledge tracing till now. Thank you.